We have to wait until that loads, right?
Yeah.
Awesome.
Okay.
Okay, so we are live, and thanks to this is the graveyard shift session, which is appropriately named Massive Stars from Cradle to Grave. We're going to start with our first speaker, who's JJ Eldridge from the University of Auckland. And JJ, I'll text you a private message on Zoom to let you know that you have 5 minutes left. Is JJ?
Yes, I'm here. I'll just share my screen.
Okay, fantastic. Hi, JJ. Oh, we can see you.
Hiya.
Great.
I can see you. It's actually quite an interesting camera that you've got there. It's like fun to actually sit there watching it as it moves around. But yeah. So yeah, kia ora everyone. Thank you very much to the organisers for inviting me to come and talk about supernovae and supernova progenitors and their evolution. And this is work, of course, I've been doing for many years, and it's going to be done in collaboration with Elizabeth Stanway and the BPAS team. So it's a mix of people from the University of Auckland here in New Zealand and the University of Warwick in the UK. And just to introduce myself a bit more, when I can actually advance my slides. Why is my computer not just, oh, there we go. Who am I? Just to introduce myself a bit more. I'm Associate Professor JJ or Jan Eldridge. Either is fine. It's just I basically recently changed what the J's stand for. So you can actually still see what my name used to be back in my previous papers, but that's changed now. My pronouns are she, her, them, they. I'm an astrophysicist, otherwise why would I be here? I'm currently the head of the Department of Physics at Auckland, and I study exploding binary stars while exploding a myth of the gender binary. And all that means is we all can agree that the universe is pretty complicated. All that means is that, you know, people are complicated too, which is always a good thing to remember for everything we do. And I work stars, galaxies, supernovae, and you can find me on Twitter. I've got a huge team at the moment. This is the team that me and Elizabeth both have. So there's myself, there's Elizabeth, who again is in Warwick. People seem to think for some reason she comes from New Zealand now, though she's still in the UK. Heloise is just finishing off being my postdoc. She's moving hopefully back to Europe. Connor is Elizabeth's postdoc at Warwick, and John Bray has just moved back to New Zealand to start a postdoc with me. And together, me and Elizabeth both have a large number of students. So we've got Max, Petra, Sohan, who has already, I think he's already given his talk, or will be giving a talk soon. Wouter, who's in the Netherlands, Sean, and also Gareth. And so Gareth is in the UK with Elizabeth. The rest are all one of my students. And we've got many other past people whose names I'm sure you'll recognize. Now, when I'm giving this talk, because I'm talking about stars and their evolution, I'm going to take it very much from my own code perspective, which is the binary population and spectral synthesis code. So as much as introducing the team, we need to introduce the other member of the team, which is the code and the group of models we use. And so I'll be presenting that as we go through, as like to describe the evolution of stars and how binaries impact on that. And then actually using it to try and show you the observational consequences and evidence that that what I'm saying is correct, because, you know, otherwise I'm just making things up. Well, I might be making things up, I don't know, but let's see if I can sneak anything in that I could just make up and just muck up the field for a few decades. But BPAS is the binary population spectral synthesis code. It was developed by myself and Elizabeth to study stars, supernovae, clusters, galaxies, and compact remnants. And it's trying to be the theoretical equivalent of multi-messenger observations. And so we make one model of stars and we apply it to observations and observe that model or those models in the same way. And we don't change our model to try and fit one observation. We try and understand if it can fit everything at the same time, and then we find places where it doesn't match, and that's what tells us what we need to change it. But we need to change it in a way that we don't stop agreeing with something else. And it's a bit more, it's a different way to what most population synthesis works, but it's what we're trying to do. And for reasons to do with the way we do our models, because we have detailed stellar evolution models, it's a big computational investment to make those models. So we try not to, you know, produce lots of greenhouse gases by burning up oil, CPU time to try and make new models until we know we get to a point where we actually need to revise them. And actually within the next few years, we're currently there, and we're now working on the next generation of BPAS. Luckily, there is, you can get it from both Auckland and Warwick, same models, just, you know, one's closer to the other. There's a Python package that Heloise has written that basically enables you to very easily access BPAS models. And actually on the Hoki website, there's all these recipes for, like, if you want to find a supernova progenitor from the models, it tells you how to do it. And so, yes, if you have a star or a star cluster you want to understand, search for it for VPAS. And of course, if you get any problems, you can always email us, and there are the main papers down there. But we've had so many papers from the team over the past few years because we've been in this exploration. Let's use our models to try and understand stuff phase. So let's get back to the topic of the talk, supernova progenitors and their evolution. So I thought, towards the end, I'll talk about some things that maybe you want to think about. The observations are starting to show we need to think about the very late stages of evolution. But it's always worthwhile going right back to the beginning, the stuff we learned as undergrads, postgrads, PhD students, the stuff we think is usual knowledge. Because, we always need to all be starting from the same place. And so we need to think about our main sequence stars, like our sun, burning hydrogen to helium. Of course, for core collapse supernovae, I'll get onto thermonuclear supernova later. But for core collapse supernovae, we know it's got to be a massive star, more massive than about 7 or 8 times the mass of the sun. We're not exactly sure how massive, because there's lots of uncertainties that go on. They're burning hydrogen to helium by the CNO cycle. And eventually you get a helium core with a hydrogen envelope. And the star becomes a red giant. If you want to know what the fancy word is for that, it's called erythrogigantism. So, you can learn that word today. I'll say controversially, and somebody asked me about this, that we don't know why stars become red giants. We know they become red giants in our stellar evolution code. We know they become red giants or red supergiants in nature. But the actual process, the physical process why that happens is uncertain. There's actually a great paper from about a decade ago by Richard Stancliffe where, to try and find out why stars become red giants, he took out the bits of physics that people thought is why stars become red giants. And you do that until the star doesn't become a red giant, because actually you can take out quite a lot of physics from your stellar model and the star still becomes a red giant. And he did find one piece of physics he removed. The problem is then he tried a different massive red giant, a different massive star, and it still became a red giant without that bit of physics. So the reason why stars become red giants is probably different for different masses of stars, and there's not one answer. You'll read in textbooks about the mirror effect because, around this helium core, you've got this burning shell, and what goes on inside the shell is different or is mirrored on the outside. But that's what's conserved, what's the physical process going on, and it is highly complex and nonlinear because stars are nonlinear. But anyway, once we've got that helium core, it collapses, and you end up getting to the point where you can ignite carbon and oxygen. So for our sun, it'll end there. But for more massive stars, above about 8 times the mass of the sun, the nuclear burning can progress further. And so you can burn your carbon to oxygen neon, then your neon to oxygen and magnesium, then your oxygen to silicon, and then you get a series of alpha additions all the way up to forming your iron core. And of course, then that's the peak of the nuclear energy binding curve, like cobalt, iron, and nickel are all very close together. And so you can't get energy out by fusion, and your 1.5 solar mass iron core collapses down from something about the size of the Earth down to something about 10 kilometers across. And so you get a supernova because you get all the energy being released. There's a large flux of neutrinos. And so if you've seen this joke before, I'm sorry, but I think it's funny. I've become old now, so I can do my old sad jokes that everyone hates. As you'll see by this really complex supernova simulation that I'm going to show you, what happens to the star when you form your neutron star. It goes bang. So you get the energy being transferred from the supernova. We don't know why. There's been many talks already about like jittering jets and other things that we know that some supernovae explode, some won't. We're not too sure. It's something that we're still trying to understand. But we know from observations that it explodes. So there's the classic project, that's been going for decades now, first initiated by Schuyler, two teams, Schuyler Van Dyke and Stephen Smart, trying to observe when you see a supernova go off in a nearby galaxy, you go, and if it's within 20 megaparsecs or so, you go into your HST archive, you find a pre-explosion image, and you see a cool red star, and you go back, and it's dead, right? So it's an X star. It's shuffled off this mortal coil, which is no more. It's good. There's enough people here that's probably old enough you've seen Monty Python, so the X-Parrot sketch still makes sense. I can't do this joke to undergraduates anymore. They just go, what? What's Monty Python? We don't know what this is. Is it on TikTok? Anyway. So this is the evidence, right? We've seen for supernova 2008 BK, we saw a type 2p supernova, we saw a pre-explosion red supergiant, and then it's gone. And so we know that this happens, and there was a neutron star formed in this explosion. So that's single star evolution. Now, for more massive stars, you do You can lose the hydrogen envelope and you can get a type 1bc supernovae. But one thing that's really happened over the last decade is many groups have been showing that binary interactions are responsible for the large number of the hydrogen-free and hydrogen-poor supernovae. Because if you think of that nice linear scheme I showed for like a single star to evolve, if we go to binaries, it gets a tad more complicated, right? And so you start off here with your two main sequence stars orbiting around each other, and one experiences erythrogigantism or gets bigger, and it interacts with its companion because it expands to a size where the gravity of the other companion can attract material off the surface of the star, and you get mass transfer. And either it's stable and the companion can become quite massive, or it can enter common envelope evolution, which is a hideous process we don't understand. So everything you ever learn about binary evolution has this caveat: we don't understand common envelope evolution, especially for massive stars. Some groups are doing it. So there's some great work coming out of the Monash group where they're trying to model common envelope evolution of massive stars, and of course many people are doing similar things. But we've always looked at common envelope for low mass stars. High mass stars, it's a bit of an open game, and understanding gravitational wave transients will also help us understand that. The reason why there's many arrows and many different pathways for binary stars is because there's many different mass ratios. So the ratio of the masses of the two stars affects what's going on, because that affects how stable the orbit is if mass transfer happens, and also the period, because it tells you, like, is the binary interacting on the main sequence? It will probably be stable. Post main sequence, it might be stable, it might not. And this is actually something in BPAS, because we have the detailed models, we approach in a very different way to everyone else, because when our star fills its Roche lobe, we know whether it continues to expand or shrink within its Roche lobe, which actually we're still trying to understand it because it's so complicated and we have so much to try and understand, because there's so much stuff that's kind of been done in a different way. So we're trying to, because we're doing things in a different way, having to learn what's going on. The real key thing that happens, though, is in most of these interactions, sure, you get some mergers, so you get a single star that was a binary, which can be confusing, but you also get these green stars here, which I know I need to change them because of color blindness, so I really apologize. But we get these helium stars where you've taken off the hydrogen envelope, and they're not Wolf-Rayet stars because they're not massive enough to drive the optically thick winds, but because of the IMF, they're the most common type of star in this mass range, and so they can produce a lot of the type 1bcs. And of course, then you get a supernova, so sometimes your binary can remain bound and you go on and you get gravitational wave transients. And just to bear in mind that a lot of this work about helium stars has also been paralleled by many others, notably Uwe Gothberg, who's like really trying to find these systems and these helium stars and find out parallels, because we don't actually know any of the helium dwarfs. We do know helium giants, where they evolved to. I'll show you some HR diagrams in a minute with this. Observational evidence for having helium stars explode as 1bcs comes from, initially it was IPTF13BVN, and this very fuzzy JPEG has this little faint fuzzy blue dot here, and actually the photometry is quite terrible, even though it's HFT, because every different group that looked at it got a slightly different answer. Slightly different answer, but we know that the luminosity is low, and this progenitor here is a very good match, because it's now vanished, as we found in 2016. It's a very good match to the binary models that we have, with a very low mass companion that we may not be able to see. Okay, but what other observational implications are there from having these binaries produce most of the evolutionary impacts on our supernova progenitors? Well, when we look at the HR diagram, we kind of get scared, because the colored tracks here are all the binary models with the same initial mass as the black lines that I've included here. Hang on, let me turn it on. Sorry. And so you can see that while it's also, there's a big range of things that can happen, it's not that bad. You can see that there is Roche lobe overflow, and common envelope takes you below the mass of the star, but then it comes across to become a Wolf-Rayet star. So the black lines are the single stars, and the colored lines, as I've said, are the binary tracks. And so you also get merger products. And actually, you've got a lot of merger products here that are actually merging on the main sequence. So we'll come back to that in a minute, what actually goes on about late time mergers. I know I've seen that, I think one of the talks following me has got 87A, which is perhaps the most example of a late time merger for any of these stars. That's always good. And sometimes you can actually see there are messy tracks like these just here underneath this 15 solar mass track. So, while I'm trying to give you the idea that there's these broad things that we know binaries do, they also do weird things. The helium stars I was talking about are actually right down here. So this is, I think, a 10 solar mass star. And you can see that, yes, you've got these binary interactions and you've got mergers. But over here, far to the hot side of the main sequence, you've got helium stars. And so here you've got tiny stars that are like very, very small next to a star that it's actually probably transferred all the hydrogen to. So the other star is probably quite luminous and much more brighter than it was, and is actually going to be outshining the helium star in the optical until this star then evolves and goes up the hydrogen helium giant branch to explode as a type 1b/c supernova over here. And of course, these are very much like the Wolf-Rayet stars, the more massive ones that have got the luminosity to be able to drive optically thick winds and be observed as a Wolf-Rayet star. But they're just pure helium, so the lines and the spectra are a bit uncertain as well. And they're only accessible from binary interactions. You can't get them from single star mass loss. Now, the great thing is, having detailed models, we can now take these models and blow them up. And actually, if we do that for every type 2 supernova we have in BPAS, we can compare the single star tracks we have for single star models, and every time you have hydrogen in your model as a single star, you basically get a type 2p supernova, right? Some of the low mass ones are a bit funny because they probably don't explode, but otherwise they look like 2p supernova. The second you put binary interactions in, again, you get a mess. And actually, if you look at the 2019 paper, we've taken these models apart and separated them out, and you can actually see different types. And even within this very simple approximation of only like about 1,000 models we ran and exploded, all with the same energy, all with the same nickel mass. So it's all these same assumptions we're putting in, and these differences are only due to the binary interactions that star had. And so like how much mass it lost, how much it gained. And so, this is something we need to consider, that a lot of the variety we see in supernovae comes from binary interactions. But we can go one further still. So with BPAS, we also predict the spectra of these stars. And so actually we can try and look at these things called galaxies, because galaxies apparently are where supernovae happen. And here, this is some work by Louis Galbany, where he's observed galaxies with an IFU, an integral field unit, to get spectra of each pixel, and he's identified H2 regions and looked at the places where supernovae have exploded. Some explode on H2 regions, others nearby, others explode pretty much where there are no H2 regions. Now, if you then go in and look at the diffuse ionized gas and the H2 regions and the supernova sites, and you take the spectra of the stars around the supernova site, you can then compare it to BPAS and compare it to the models that we get out for the supernovae that we should have for these different supernova types. So it's what many people can do to try and, a lot of people, if you've got resolved progenitor studies, you can actually look at the nearby stars. This is one step beyond that, where you're actually using the ionizing radiation. So actually you're measuring the number of hot stars you have in your stellar population to see if that tells you something about the supernovae. Because if everything I've just said about 1bcs coming from these hot helium dwarfs that become helium giants, there should still be hot helium dwarfs around there when that star is exploding. Other stars that haven't exploded yet, but are still producing ionizing radiation. And we can put this picture together. So here we have, for the Louis Galbany sample, the age and the metallicity of all those different supernovae fitted from the ionizing lines or the emission lines in the nearby local stellar place. So of course it may be a runaway star, but we tried to pick a big enough aperture that it was getting the average age and the average metallicity of stars near that supernova site. We did the fit using single star models and with binary models. And there are two differences you can immediately notice. One is, in general, the binary stars are higher metallicity. We don't need to go to lower metallicity to get the hotter stars, to get the higher energy ionization lines. We have those helium dwarfs that are actually much hotter than main sequence stars, 100,000 degrees Kelvin. We also have ages that are a lot older, so 10 million years old and older. Whereas all the single stars, you have to have the very hot luminous O stars and Wolf-Rayet stars that only come at very young ages to explain the emission lines we see. And we know that, massive stars have to have a minimum lifetime of 3 million years. So there's a problem there. When you put masses onto this, you can see that, of course, most stars only have masses less than 20 solar mass, most of the progenitors. There's a few beyond that. Error bars are admittedly large, right? So this is actually difficult work. And you can see, though, the same trend is there for the type 2s and the 1bcs, although type 2s tend to also have a lower metallicity tau. So this is quite exciting, because now we can say that actually type 1bcs and type 2s are coming from the same stellar mass range. We are missing those very massive stars, but then they could be rare, and this is something we didn't actually look in with the rates. But this ties into something else about the evolution, which is a bit, which everyone's getting excited about, because do we actually get a supernova when we form a black hole? We don't know. But, you know, a lot of people have been doing a lot of work, for example, Thermonuclear, where you're looking at the initial mass of your model, and you take it to core collapse and you see if it explodes or not. And it's around about that 20 solar mass limit of about 10 million years old for the star that you start forming black holes at core collapse rather than neutron stars. And actually, Togolda's shown that it's to do with the type of nuclear burning during carbon burning as to whether you get that neutron star or black hole. So there's still a lot of work here to do, though, because you can see if you use different physics, then you get a different answer. On the left is a plot I threw in because it comes from my thesis, and actually I did something even simpler. I just put one pho of energy, 10 to the 51 ergs, into my model, saw how much energy I could remove, or how much mass I could remove from the star and what was left. And so this is what is left. And again, you start getting black holes or massive neutron stars at around about 20 times the mass of the sun. So that's something else we don't understand, that very end stage of evolution. Okay, I think I've got about 2 minutes left, and I've got too many slides. So I'm quickly going to jump through what I was going to say, which is about thermonuclear supernovae. We know type 1a thermonuclear supernovae come from binary star systems. We know they come from white dwarfs. We know white dwarfs on their own can't explode. So there's got to be some sort of dynamical interaction. And there's got to either be a single degenerate or a double degenerate pathway. Within BPass, with various constraints we're comparing to observations, we're finding that the single degenerate pathway, because our mass transfer is different to that in rapid population synthesis codes, the single degenerate pathway is the main one, not the double degenerate pathway. Whether that's correct or not, that's just some physics we put into our models. But we do match, if we try and take account of the universe and how it's evolved over time, and we look at the delay time distribution, we can match the rates of type 1As we see versus redshift using this channel, which surprises me. Okay, I've just got a chat message which is probably telling me 5 minutes left, which probably came in 5 minutes ago, so that's okay. Okay, I'm going to skip past this because I've talked too much, and that was just showing stuff going on. So just in the last couple of minutes, I'm going to say, what else should we be worrying about? So we've got this general picture. Stars evolve, you've got the core going on, that evolves all the way to iron core collapse, or to whatever core collapse it goes to, and you've got the envelope on the surface. The amount of stuff there is probably impacted by binary interactions. Binary interactions can impact on the core. They typically make the cores less massive, although there are certain regions of binary interactions which actually give you more massive cores without a stellar merger, which is something that rapid population synthesis codes kind of miss. You can ask me about that if you want to, because it's to do with convective zones. It's really exciting if you like stellar evolution. But the things we need to worry about with other things to do with stellar evolution, one is nuclear evolution. So we have this picture maybe that stars chug along nice and smoothly when they get towards the end of their lives. But good work by Stan Woosley and collaborators shows that, for example, here, low mass stars, when they go near the end of their lives, really don't evolve nicely on a temperature density plot, right? This is the central density and central temperature. And they're all over the place because the nuclear burning is extreme. It's happening in degenerate matter. And so this must have an impact on the surface and the final event of core collapse of the star. And so this is something we're still trying to understand, and something, if you see a late time event, it may have been caused by a low mass star going through some of these very uncertain flashes of nuclear burning. But then at the high mass end, we know there's also pulsational pair instability, which causes problems. When the star goes into a certain regime where it starts making pairs, reduces pressure support, and undergoes these really large flashes, which again, we suspect produce lots of output. The other thing to worry about is late stage mass loss. There's a lot of evidence coming out from observations that stars suddenly change their mass loss or lose mass loss in the last few years or centuries of their life, and it changes. Now, this is quite difficult to try and explain, right? Because if you look at models that do very rapid changes, it may be nuclear evolution causing enhanced mass loss, but there are other things that can go on. So Heloise recently was trying to explain a superluminous supernovae, and you had to lose a large amount of mass just before it exploded, and she thought, oh, it's going to be binary interactions. Went through the BPass code, couldn't find any that fitted the bill. But she did find a couple of models that go through this evolution, and just as they're getting to the end of its life, the surface conditions change. So BPAR switches on a different mass loss rate, and it suddenly starts losing a lot of mass. And that was actually enough to explain the mass loss that you needed for that event. So, not always do we actually need to have a physical mechanism of something causing extra mass loss. It may just be that there's always a continuum of stellar types that can suddenly change when you get there. Nothing is hard and fast. It's not like a Wolf-Rayet star or a red giant. There can be things that are in between, or something that's in between a WN and a WC star, so the mass loss rate is changing. Having said that, we are looking at GW 170817, and we're finding some really fun, really late stage evolutionary effects. Like we're finding that the helium giants can interact with the companion and actually be undergoing Roshtov overflow as a helium star when they explode. What that does for the CSM and for the eventual supernova, no idea. We've also found some stars that go through 2 phases of common envelope evolution, which is a bit weird, but only happens because we've got the detailed code. And then sometimes, again, with mergers, things like 87A, we can find them. And, there's things where you lose lots of mass, but then you gain a little mass. And so your merger product may not be like a red giant. It might be something unusual. And there's just a case there I'm talking about. And of course, there's many other things I can mention, like oscillations, tidal spin up and spin down in binaries that could also produce late time effects, which is actually kind of like, even though we know pretty much there's still uncertainty about the evolution before we get to the very end stages, that end stages is a really rich area where theorists have got lots of ideas, but we're not too sure what could be going on. But it's supernovae, observing them and their remnants, that's going to tell us about that very last stage of evolution, which is actually why I'm interested in learning about all this at this meeting. There's my list of slides, list of comments. So binary stars need to be considered, late stages still need to be understood, and there's lots of things we need to understand. And so thank you for listening to my talk. I'm just going to put up my YouTube video of binary evolution just at the end to hypnotize you while I answer questions if anyone has any. So thanks for listening, everyone.
Okay. Thanks, JJ. That was a great talk. Do we have any questions from Zoom?
None from Zoom.
Not from Zoom. Oh, I see Professor Kertzendorf there. Super eager to ask a question. Okay.
The perfect state. I mean, it's 8:30 here, and then I had a couple of beers, and I think that's the perfect sort of like environment to ask provocative questions. So, Jan, it's pretty usual, a wonderful talk, like amazing talk. And the only thing I want to say, like, you're wrong about the 1As. I mean, clearly they can't be seen together. The main thing that I want to ask you is, like, when we had this wonderful talk about tests today, where they were very bad at the branding, but I ultimately asked them later, and they said for 71As, they rule out red giants as a progenitor. They don't rule out main sequence stars, but they rule out red giants. We've never seen a companion star. So if you feed this into your model and say, like, anything that is bigger than a white dwarf is ruled out, what do you then get?
Okay, so that I haven't seen that information. And so one of the questions is here that at the moment we don't actually follow the explosion. We're only following the mass transfer onto a white dwarf when we get to that size. Whether it actually explodes when it gets that size and what. Sorry.
You know the companion size, right? At the time of explosion.
Yeah, because you can see it on the light curve. Is that what you're saying?
No, I'm saying in your models.
Yes, we can. Well, no, so we don't know when the explosion is. So we can say it's any time we want. We could say, oh, we put all this mass there, but we have to wait for the other star to die for it to explode, because we don't study both stars in detail at the moment, which is one of the things we really need to do. So at the moment, we have a very simple, I will admit, we have a very simple mechanism for type 1As, and it's something we need to work on. We don't get enough we still get some double degenerates, and actually their rate is increasing. But when you look at trying to match the, let me stop this video, hang on. Let me go and show the plot. So if we put this in, our double degenerates are about 10% of this line today, because it's down here and it's actually rising up. So you're right, and this is something we need to work on. So I can say it's single degenerates, sorry, in our code, but it may not be correct because we haven't done that test. What's actually happening is, so go on.
Go ahead.
And it's all to do with the mass transfer. So we don't even know if the ones we're predicting will actually go and what goes on with the future evolution. So you've asked a very good question, and I'm going to throw my hands up and say, well, who knows? We're probably not getting them right. We're getting the right numbers, but we may not necessarily have the right stars exploding. So we're having them exploding at the right age, at least.
I mean, one reason why you could, I don't know if this is true, but one reason why you could not be getting enough of the double degenerates is because the binary systems coming out of your common envelope may be too wide, right? Because if they're narrow enough, gravitational waves take over, and then they basically do the job for you. But
yeah. But then also, I mean, so common envelope is a huge problem. Yeah, and so we do know we need to look at it. And actually, Heloise is putting in many applications to try and look at it, and it's one of the things we really want to look at because we want to look at it with a detailed code, not with rapid population synthesis. The thing about that is, though, with actually, I would need to reflect on this, and I may answer it on Slack, because you will, with the double degenerates, get a different delay time distribution, and how that matches with your star formation history of the universe to match that rate through cosmic history. That's something that may also have some constraints. But yeah, this is something, it's really useful to know those observations, because I've still got to look through a few of the talks from earlier today. I'll go and review that and we'll look at it. So thank you.
Thank you very much from Boston to New Zealand, and we'll miss you. We miss you here.
Thanks, David.
Yeah.
I see.
No worries.
I see Vikram has a question. Let's allow it, but only if it's brief. We don't want to get too. I guess it's late already, so who cares?
Okay.
Go ahead, Vikram.
Anything goes.
Thank you. Can you hear me?
Yep.
Yeah. Okay. JJ, that was really nice. So I guess I have a simpler question, maybe. So there are all these nice, beautiful models that you do of binary evolution. We already know of single star evolution and massive stars forming like Wolf-Rayet stars and stuff. So, and we also have some idea of how many Wolf-Rayet stars are there in the galaxy. So I'm just wondering, do you get the right number of Wolf-Rayet stars with the single plus massive star binary plus binary evolution? Do you get how many more in binary compared to single one way or the other? And then how do you expect most of these 1BCs to form, from single massive stars or from binary Wolf-Rayet stars that are lower mass?
1BCs are basically all coming from lower mass stars in binaries.
Oh.
The one exception is 2017 EIN, which I still have to look at. But a majority, right? That's what I'd say. But when you look at I mean, that's a really good point with the Wolf-Rayet population, the red supergiant population, the massive star population.
Yeah.
We do that comparison in BPAS as well. So when I'm talking about this binary evolution, it's backed up by the fact I'm not just talking about supernova progenitors and the supernova rates. We've done the comparison with the Wolf-Rayet populations and everything else. So it all kind of fits together in like almost like a conspiracy theory type place. We're trying to make it more rigorous, but that's a really good point. So I'd have to give you I'd have to actually go and work out the exact numbers to tell you that. But yeah, so we know that most Wolf-Rayet stars, a lot of them are in binaries as well. But Wolf-Rayet stars may not be the most common progenitor of type 1BC supernovae.
Oh, so what is?
It's the helium giants.
Okay.
Thanks, Vikram. That's a really good question. Thanks, everyone.
Okay, so we're going to move on to our next speaker, which is Katie Ockenhoff. Hi, Katie.
Hi, everyone. How you guys going?
Hi, Katie.
Hey, Katie.
Good to see you. Wish I could be there.
You were here.
Okay. Okay. Can you see the slides and everything?
I can.
Yeah.
Yes.
All right, awesome. Okay, so thank you so much for inviting me to be able to talk about essentially using supernova remnants to understand stellar death. Of course, I would love to be there, but a new binary companion joined me, so I couldn't actually attend this time. But before going into understanding or like this talk, usually because I know it's really late and everybody probably wants to go off home or to get their beers, I'll give you kind of the summary of what my talk is going to actually cover. So we all know that supernova remnants are kind of the long-lived structures of supernova explosions that are kind of a useful means of to test and constrain and understanding of how and which type of stars die. And in particular, we can actually now kind of tie supernova remnants to their explosive origins and use their properties to understand many aspects of stellar death, which includes the mass of the stars that undergo supernova, how these stars actually explode and throw out their ejecta, and for example, probing their compact objects. And in particular, in this talk, I'll talk a little bit about magnetars, but I know that there is a number of other talks, say by Tyler and other members of the conference group, that will also touch on this part. And so, of course, before going into all the details, we kind of need to give a bit of background. So in the last few years, we've actually seen a complete coming of age associated with our abilities to detect and follow up a wide variety of transients, including those that are associated with supernova explosions. And so with both current and future optical surveys, we expect this number to only increase as we enter kind of the next era of data-intensive time domain astronomy, which will lead to a wide variety of interesting discoveries that will further our understanding of these and other fascinating objects. However, even though our abilities to kind of detect them have significantly improved, unfortunately, they're located at distances that are just not able to resolve the explosion very well. And it can actually be quite difficult for us to kind of see the immediate surroundings of these stars that are exploding unless they're pretty close to us. As such, it's kind of ideally what we would want is to detect supernovae that have occurred much more close to us to be able to kind of probe these properties. But unfortunately, it's not always that easy. We know that supernovae that occur nearby to us are actually quite rare. And in fact, in our own Milky Way, we only have about 8 supernovae in 2,000 years, which is much less than what we expect from the 2 to 3 supernovae per century per galaxy that we should expect. And as such, this kind of makes it difficult to study many of the aspects of the explosion directly, even though many people are trying their hardest to be able to do this. However, I'm going to try to make the case that actually supernova remnants are actually a unique opportunity, provide us with a unique opportunity to study these supernova explosions and their dynamics on much smaller scales that are inaccessible to us when observing supernova in very far galaxies. And in particular, I will talk about essentially using these supernova remnants as a population to try to answer some of the major questions that we kind of all have and what leads to kind of the great conference that we're actually having at the moment. And so starting off with this one, we want to know what the masses of stars that undergo core collapse. And, I'm very lucky to be able to follow JJ because JJ kind of covered a lot of the really amazing work that they've been doing and also really kind of set the stage for understanding this. And what was kind of shown in the previous talk is that, one of the most uncertain aspects of stellar evolution is essentially the link between the nature of a supernova explosion and essentially their progenitor stars. And, as we know, right, we think that massive stars undergo core collapse, once they hit the nuclear burning that leads to an ion core, they will then collapse, producing the explosion. Of course, this is the general summary. However, as was shown in the previous talk, we know that the type of explosion that a star undergoes depends on a number of variables, and especially depending on whether we actually have an observable explosion or whether we see a compact object such as a black hole or a neutron star, depends on the mass of the progenitor, whether it's found in a binary, as well as metallicity and other aspects that are kind of constraining. And so as such, we saw that there's been significant theoretical work to try to really determine which stars undergo core collapse and produce a supernova of a given type, and which ones of those produce compact objects. But observationally, there have been a number of attempts to try to identify the progenitor stars of core collapse supernovae using preceding space and ground-based images, and even JJ touched on a handful of them before. However, the issue with this type of study is that it's actually quite hard, right? We're actually limited by a number of factors, including the supernova rate in the local universe, the depth of archival or current observations. And really, as a consequence, we only have a handful of supernovae that have detections of their progenitor stars prior to the explosion, with these studies suggesting that there is actually a deficit of high mass supernova progenitors above about 18 to 20 solar masses. However, as we saw before, theoretical studies of these core collapse explosions predict that even higher mass stars should also still explode, as seen here, for example, in the work by Tuglador, where essentially the green vertical lines in the different core collapse models show that that are shown by the horizontal rows, we actually expect some supernovae will produce observable explosions, and some actually won't, and that they actually will instead implode and produce a black hole. And so one possibility is that the lack of progenitors that we're seeing above about 8 to 20 solar masses from the supernova constraints, it could be that actually this is a natural result of the fact that a fraction of massive stars are actually expected to implode and form a black hole without a visible supernova. However, since we also expect observable explosions based on some of the theoretical models we're actually seeing, the natural question that now arises is, where are the core collapse supernovae from those high mass stars thing? And I actually think that supernova remnants can actually try to help us answer this question that's complementary to the work that's been done from the supernova case. And so one way that we can actually probe the progenitor properties of supernova remnants is by essentially looking at the stellar populations directly around a supernova remnant. And we can actually use both the age and mass of these stars as kind of a proxy of the age and thus the mass of the star that produced that object. And this is actually kind of building on the work that Carlos had actually started doing. And so let's take out one of our favorite supernovae, supernova 1987A, and essentially draw a box around that, the region of the supernova remnant to look at the stellar populations. And what we actually get here is essentially star formation history as a function of age. And what we can nicely see in this plot is that at least the stars that are surrounding supernova 1987A have a burst of star formation that occurs around 10 mega years, which actually corresponds to about 15 solar masses. And when you compare that to the constraints that you actually get from independent constraints of the progenitor of supernova 1987A, we find that this is actually consistent. And so we can actually, the power of essentially using the star formation histories and combining them with other external information can really help you kind of narrow down essentially what, or put constraints at least on the progenitors of these stars that were actually, that produced the supernovas when they occurred. However, as was shown previously, we need to understand the expected lifetimes of these massive stars. And in particular, we know, as JJ pointed out, is that, you have single stars, where their lifetimes are approximately between 3 to 50 mega years, but binary interaction can actually extend the lifetime of the star. And while low metallicity environments, you can actually maintain rapid rotation of the massive star, which also extends their life up to like 100 mega years. And so one really needs to kind of take those considerations when trying to do this type of study, where you're studying the stellar populations, to really understand our expectations for the delay time distribution, essentially, of core collapse remnants. And so what we actually did is that we actually considered the star formation histories of around supernova remnants in the small Magellanic Cloud. And so we did this because, it's face on, we get to see the full population of our supernova remnants that we have, and we also had the star formation histories seeing this. And so what we can actually do is play this same trick again, looking at the star formations that we have and comparing the results that we get from that to independent constraints on the progenitor from X-rays or other wavelengths, and be able to kind of put together a picture of what the properties may be. And so here I pick a very obvious case where we actually have the star formation history, again, as a function of time for a particular remnant. And we find that in this case, at least, that, there's a peak of star formation that occurred about 30 mega years ago. And if you can consider that the progenitor was perhaps maybe a single star, then it should have had a mass between about 8 to 13 solar masses. Of course, if you add the binary case, it does change slightly, but essentially it's a lower mass star. But I was a bit sneaky when showing this plot because, of course, I picked one that was obvious to show how it can actually be quite, not easy, but at least more obvious what the progenitor mass may be. But not all of them are this distinct and beautiful and concrete. And sometimes you actually get essentially multiple bursts of star formation at different epochs. And so in this case, it actually can be much harder to say whether, yes, the progenitor star was of a given mass. And so you actually have to assign a probability that a particular mass progenitor associated with this. And so this is what we actually did. We did it for the full population. And what we essentially we tried to represent that the progenitor or the probability that the different supernova remnants in the SMC that had been classified as a core collapse or that had star formation and other information that was consistent with a core collapse, we tried to represent whether the probability that they came from, say, a small, medium, or large progenitor, essentially by the size of the circle that we have here. And by looking at this plot without looking at knowing all the details, you might notice that most of the larger circles tend to occur in the higher mass part of this diagram of the mass distribution, suggesting that a large fraction of core collapse remnants probably arose from masses greater than 21 solar masses. So actually, maybe we are seeing observable explosions that produce supernova from the supernova as well, consistent with theory. But of course, you may wonder where, like, what's happening with this? Is this kind of, does that mean that maybe the SMC is top heavy? Well, we actually kind of had a look at this, and we actually found that the distribution of the progenitor masses we get seem to be consistent with kind of salpeter. Of course, the uncertainties are pretty large on this, but it does overlap on this. And this kind of, again, is consistent with some of the work that JJ and collaborators have done, where they've looked at the stellar populations around different supernovae, where they actually seem to suggest that actually you can even find progenitors from supernovae that are actually much larger than 18 to 20 solar masses that can produce observable explosions. But of course, this is one galaxy. But we know that there's other galaxies that these occur in. And so, you know, what about other galaxies like the LMC, for example? And so the PhD student I'm working with at the University of Melbourne, Sonia Penkov, is actually looking at this right now. And the reason why we're looking at the LMC is that you actually have much more, a number of different type of supernovae, right, where there's nearly 70 confirmed in the LMC, where about 12 of them are known, and about 7 of them have star formations consistent with core collapse. And the nice part is that we can try to see how metallicity between the two galaxies can actually affect the results that we actually get. And so Sonia has been doing a really great job by looking at these populations and actually has done essentially the very similar analysis that I presented before, looking at those star formation histories, and in particular tying it together with the independent information that we get from X-rays or other wavelengths. And we essentially produced a very similar plot, right? Where again, the probability that a particular remnant arose from a particular mass is shown by the sizes of the circles that we have here. And again, looking at this plot, we seem to find that at least it's a more higher fraction, or that they seem to come from a larger mass distribution, but also from this medium mass range as well. And so essentially our conclusion from that part is that actually it seems that, again, the large fraction of LMC core collapse supernova remnants arise from progenitors greater than about 12 solar masses. And so we're kind of trying to understand more about kind of the properties between the SMC and the LMC, but this is currently what we're working on at the moment. So since we kind of understand that there's now, you know, we know the masses of the progenitors that are, or have an estimate at least of the masses of the progenitors, the next step to ask is, well, how do massive stars actually explode? And so, you know, we're really kind of now at a great point in terms of studying supernovae, because 3D simulations of this violent event is now getting to a point that one can actually make a massive star explode, which is wonderful. But more importantly, at least for an observer, they can actually start making predictions of observables that we can actually test. And so, for example, they are actually predicting that, you know, you can have large scale asymmetries in the ejecta distribution, that you can predict the neutron star kick velocities and say that they're comparable to what we actually see when we measure them, and also kind of predict what types of properties we expect from both supernovae and the remnant themselves. And so this is actually really a right time to start looking at these large populations of supernova remnants and actually compare them to the populations, and using these to understand these about the explosions of themselves. And so you've probably seen this plot before, you know, which is one done by Laura Lopez, where essentially we can actually show that the overall morphology of core collapse supernova remnants are asymmetric and elliptical. So we can actually use visually their shapes to be able to kind of put a constraint of whether something came from a type 1A or a core collapse. And so while I show this nice plot, one thing you may be wondering is, well, what about the morphologies of core collapse remnants in different galaxies? How do they change as you move from different galaxies, especially taking into account that maybe the progenitor masses differ or other properties can actually affect the supernova explosions themselves. And so taking Laura's plot and trying to highlight here, where in light blue corresponds to the LMC supernova remnants, light blue and orange, and the red and darker blue correspond to Milky Way remnants. We find that they actually have, in those different populations, we find that they have similar properties in the sense that there's no significant differences between the morphologies we see of the core collapse or the type 1As they seem in these two galaxies. There may be as a hint that they're just very quite similar. But what about very low metallicity galaxies like the SMC? Do we actually expect to find that we would that they would then fall naturally on the same population that we actually see here? And so trying to answer this question, the first thing usually we're trying to do is, again, have a prediction. You know, what are we expecting to overlap, and does this match our prediction from theory? And so, you know, it has been suggested by a number of papers. Of course, I haven't listed everything here, but essentially core collapse supernova or supernova remnants found in low metallicity environments tend to be more asymmetric. That's kind of the expectation that we have. And this is shown essentially or confirmed in some aspect by looking at some of the work that was done by Laura Lopez on ITK 25, where they find that essentially the supernova is very asymmetric compared to the population. This is what's shown in green on her lovely mirror asymmetry plot. But also when you look at other supernovae, so not supernova remnants, but like say broadline type 1C supernovae, you tend to find, which are thought to come from jet-driven or asymmetric explosions, you actually find that they tend to be in much lower metallicity environments. But we can actually test this with the supernova remnant population. And again, this is what Sonia is actually doing now. And in particular, she's looking at the supernova remnants in, again, the SMC, because there's about 23 of them, which of about 18 actually have Chandra X-ray observations that we can actually use to work out what the morphologies are. And so what Sonia has actually been doing is calculating the multipole moments of the X-ray surface brightness associated with these supernova remnants, and essentially calculating the powers of the multi-pole expansion. Because what this gives us is essentially, or it encodes information about the ellipticity of the source, as well as deviations from mirror asymmetry or mirror symmetry. And we can essentially now do, which is essentially the same study that Laura had done when she was in 2009 and 2011. And so here's our kind of current preliminary work, where essentially now she has taken essentially all the morphologies that she calculated doing this same population. And what you notice again is that actually on this plot, we find that most of the core collapse remnants fall in are very elliptical and very mirror asymmetric. And so, and they kind of tend to cluster up in this top part up here. This line here that we have here corresponds to actually the difference between the type 1As and the core collapse that Laura had actually highlighted. But what you may notice is that one of our, more famous supernova remnants in the SMC 0102 is sitting down below this line. And we know that it's very circular, it's very symmetric. And so that's kind of an interesting thing. Why, if this is classified as a core collapse, I know there is some discussion whether it may be also a type 1A, but if it's a core collapse, why is it much more circular? Right, because it is quite different from the population that we actually observed there. In addition, when we did our star formation population study, there was one supernova remnant that we said was maybe a type 1A based on its external properties plus its star formation histories. This one that's sitting up here, HFPK 334, but this seems to have a morphology consistent with core collapse. So this suggests we may need to go back and get further observations to understand these properties. But what we were interested originally was trying to understand essentially, how does it compare to the to what we see in the LMC and the SMC, or LMC and the Milky Way, should I say? And what you may notice here, what we've done is essentially plotted everything over the work that Laura had done, where you're looking at the type 1A, or like the Milky Way and LMC remnants. And what we find is essentially our supernova from our SMC, which is shown by the green squares, are actually tend to be more asymmetric and more elliptical than the rest of the population. Of course, there's some overlap, but there does seem to be some trend here. And so what this may suggest to us is that core collapse supernova remnants in the SMC are more asymmetric than those found in the LMC and the Milky Way. And this may be connected to essentially, the star formation, to the metallicity. It may connect to the more that you may get more binaries in low metallicity galaxies, and really try understanding the different populations. But this is a very preliminary result, and we're still trying to understand this part. So I know I probably have about 5 minutes left. And so the last part that I'll kind of cover is trying to connect core collapse explosions to the properties of their compact objects. Of course, we really, this is a thing that we're always trying to do. But in particular, I'm going to talk about magnetar remnants, and in particular, building on some of the work that has been done by a number of members of our community here, but by looking at essentially at the population of magnetar remnants and comparing it to the population of neutron remnants that show neutron stars or even without. And so in our Milky Way, LMC, and the SMC, we know that there's about 37 known magnetars, and of these, about 40% of these actually have secure supernova remnant associations. And so this is actually a perfect time for us to try to actually take those supernova remnants that actually have secure associations and try to really constrain whether the properties essentially of the magnetars when they're formed, and understand essentially their supernova remnant properties as well, and see if they're different from what we see from other neutron stars or supernova remnants with neutron stars or without. But of course, we need to understand our expectations in particular, because if, for example, if we have a neutron star and it's born rapidly rotating, what we're expecting is that this will cause an efficient dynamo, which actually will amplify the magnetic field that we expect to up to 10 to the 17 Gauss. So particularly to the magnetar magnetic fields that we expect. And so if you, as a consequence of this rapid rotation, neutron stars that have an initial spin down period of about 1 millisecond will have a rotational energy of 10 to the 52, suggesting that maybe that these explosions, which produce these highly magnetized objects, must be much more energetic than, say, normal core collapse supernova explosions. And so if you have a much more energetic supernova explosion, and you have this magnetar at the center power, spinning down, then we would actually expect that the magnetar will then be able to power the associated supernova or even the supernova remnant. And in fact, magnetars have been suggested to power the light curves of supernova rated transients, such as long and short duration GRBs, and even superluminous supernova. So here, for example, is some of the work that has been done by Matt Nichols, but there is a lot of other work that has been looking at that. However, if you have this really large, huge energy reservoir associated with the magnetar explosion, this would affect not only the initial transient, but also the long-lived supernovae. And so the question is that do magnetars also affect their supernova remnants? And so the predictions we have here is essentially, we expect that then their explosion energy should be greater than 10 to the 51, and they should be much more extended than supernova that are found in similar environments. And so this is what we actually did. This is what an undergrad at University of California, Santa Cruz, Orion Iger, looked at. Essentially, they tried to look at the radii of these supernova remnants of both the ones that have magnetars, the ones that have CCOs, neutron stars, and ones that do not. And they found essentially that actually they're not significantly extended compared to other supernova found in similar environments. Which is quite interesting. Then, of course, we want to understand whether the morphologies of those remnants tend to be different in any way. And again, we kind of calculated the multipole movements to work out whether something was more asymmetric or more elliptical. And again, we have essentially shown here by in red is the magnetar remnants. And we find that they're consistent with the population, right? There's no obvious trend where maybe they're more asymmetric or more elliptical than the general core collapse population that we actually observed. And this is also true for the ones that when we're comparing to LMC or Milky Way. Of course, we want to understand the energetics because that's another way to constrain it. And what we essentially find is that we calculated the energetics of all these different remnants, and we find that, again, they don't tend to actually deviate significantly from that of other core collapse, which is also consistent with what a lot of other people have found while studying these in the literature. And so essentially with that now energetic calculation, we can actually even compare them to superluminous supernovae or other ones that are powered by magnetars. And what we find is that the magnetar supernova remnants tend to be unenergetic or under-energetic versus, say, superluminous supernovae or 1b, 1cs, or the explosion energy we get from that, which may suggest that not all magnetars are born rapidly rotating, or maybe they don't all power superluminous supernovae or other magnetar-powered remnants. And so what this kind of can lead us to the conclusion is that maybe not all magnetars are formed by rapidly rotating neutron stars and are produced kind of in normal core collapse supernovae. But we're still kind of solidifying these results here. And so I know that we're kind of at the end of the time now. I see that there's some chats coming through. And so here I'll leave my summary that supernova remnants, particularly in population studies, can be used to really answer a lot of important questions such as these ones here. So thank you.
Are there any questions in the Q&A?
We have one from Dan here.
So I think we covered that. Okay. Anything on Slack?
No.
Nope. Okay. Any questions from the room? Yeah, you see the question.
So how did you estimate the supernova explosion energy for the different supernova?
So we essentially fit the supernova remnants by extracting their X-ray spectra and fitting them with the best possible thing. And then, of course, we have to assume that it's set off, that they're in set-off phase to be able to put constraints on the properties of this. So we know that this may not be fully the right way of doing it, but it provides us the best constraint that we can on that. And we do this in a consistent way where we use all the use the same type of models to try to constrain that and compare those to what we get in the literature as well.
Okay. There's a question from Sumit on the Q&A. He asks, he's really surprised that supernova remnants that come from progenitors less massive than 12 solar masses are rare, and he's asking if that conflicts with what's expected from the IMF.
So that's a good question. So I would have to think about that because that's a really good question. So I think we do get some supernovae, but it may just be we're missing them. Of course, not every supernova is actually observable, especially Sumit, from your work. You showed that the visibility timescales are quite different. But we need to think about this a little bit more, try to understand why we're missing these. I agree that it is interesting from that.
Okay. Does anybody else have a question? I have a quick one. Is that okay? Oh, there's one from Summer Starfield. Okay.
More of a comment.
More of a comment. Summer wants us to let him know when we understand common envelope evolution. Okay.
All right. Okay, we've got some time, I think. Maybe at the next conference.
Sure. By then it will be clear. I just want to point out, is the 102 like the most symmetric core collapse supernova remnant out there?
Yes, it is. It's like crazily thing. So let me go back to the plot.
Pretty round, yeah.
Yeah, it's absolutely crazy from it, because if you used essentially, hang on, let me put it here. It's actually hidden behind the thing that we actually plotted here, essentially the key. And so it's really, really symmetric.
It's over here.
Yeah, it should be over here. Sorry, I realize now looking at that, I should have fixed it. But, oh no, it's here, sorry. It's over here. Sorry, it's up here.
Each of you wanted to? Does anyone know what is up there?
1,500 years.
No.
That's what I was wondering, whether the asymmetry increases.
Just
With age.
So it does, the asymmetry does increase with age.
Yeah, well, they're like, that they're interacting remnants, the asymmetry increases with age.
So we do find that in radio, at least we did that, an undergrad at Ohio State looked at this, and you do find that as they get older, they tend to get more asymmetric. But one thing we are going to look at is seeing if we can somehow estimate the ages of these, or at least take the ages and see if we see that it actually falls very low compared to the rest of the population as well. But we only just recently got this plot, but yeah, we were kind of shocked just how, well, just looking at it, you know, it is amazing just how symmetric it is. And if you followed this idea of looking at the morphologies as a way of classifying it, you would actually be quite surprised that that's a core collapse. So we're still kind of puzzled, and of course we're always happy to hear people's suggestions from this. We're very open for that.
Okay, we have to move on. So our next talk is by Miroslav Filipovic, and it is a contributor talk, so it's 15 minutes.
Yeah, guys, can you hear me?
Yeah.
Okay, let me try to entertain you over the next 10-15 minutes before you get into capable hands of Manami Sasaki, very capable hands of Manami Sasaki. And let me show you an object which I'm sure that the Katie would like to put on her graphs, graphs that you've seen over the last 10-15 minutes. We think we found a very cool object, which shouldn't be a big surprise as it was originally when we saw that. But let me just remind you that, guys, we have a new tools, we have a new toys, and that's the new generation of radio telescopes. And I can promise to you over the next few years a small boom in a number of new generation, in a number of new supernova remnants, mainly low surface brightness and the SNRs showing up in a complex regions. This is just the ASCAP, Australia's Square Kilometre Array Pathfinder, where we are doing a number of different surveys, but as well Meerkat, EVLA, LOFAR, and GMRT are showing a great progress in detecting the new supernova remnants in our galaxy and Magellanic Clouds mainly at this stage. Let me very briefly remind you that there are actually something which is called hostless intergalactic supernovas, and the definition is that it should be about 10 kiloparsecs away from the fringes of any galaxy. But as you can see on the right-hand side, the H1 image shows that the galaxy itself is much bigger, so we have to be very careful when we talk about what is the real hostless supernova. I've seen a couple of other examples which are much better in one of the Able clusters. So we do see these guys, and the main question is, all right, where are they around us? So we think we found one which is almost halfway, 1/3 way between the large Magellanic Cloud and the small Magellanic Cloud, where you can basically see the where here is this object that we found. I'll show you. This is small and large cloud, and when you look into a H1, again large cloud, bridge, and the small cloud, it's just off the LMC. But when you look a little bit deeper, it's actually part of the most likely part of the LMC envelope, H1 envelope, and we can see even some clumps, H1 clumps in that direction. So our latest ASCAP survey of the LMC, this is where we found this object in the bottom left corner. The object looked like a ring, low surface brightness. The distance is about 2.5 degrees from the tip of the 30 Dorados region. And if we assume that this is an LMC object, it should be about 1.7 kiloparsecs away from the main body of the LMC. Quite beautiful. Also, let me put you in perspective that the stellar envelopes of both LMC and SMC are quite big at the moment, as you can see. There is plenty of stars, LMC stars nearby and all around, but there are also stars which belongs to in line of sight belongs to a Milky Way as well. So one of the objects that we discovered over the past couple of years, we call them odd radio circles. And when we discovered the object that I just showed you, and which I'm going to talk over the next few minutes, we found a number of other relatively similar objects in our ASCAP surveys, which we call them odd radio circles, mainly rings. So at the beginning, we thought, that, is this an artifact? And we very quickly found that definitely not artifact, low surface brightness. And we ran out, through all sorts of ideas. And I'll try to show you some of the examples. So this is our early finding of this one of the particular object. And very recently, a couple of months ago, we got a high resolution meerkat observations, which we are definitely sure that this one is another supernova remnant, and it must be, something a bit more extragalactic. So let's go back to my runaway LMC SNR, or at least we think it could be LMC runaway SNR. One of the first things was after we detected this object in the ASCAP survey, we went to other radio telescope ARCA that was on our disposal, and to some extent, I was surprised to see that we can see this object in the higher frequency at 9 gigahertz. And this was absolutely fantastic, because that can give us a good idea on the spectral index. So let me show you a little bit more intimately what is this object and what is surrounded. So in red, in this RGB in red is optical image from SMASH. Green is our radio image, and we even have a quite good X-ray images, XMM, and also we check the Eros Zeta. So nothing we can see in Eros Zeta and in XMM, apart of the couple of objects. One of them is a nearby star, which I'm going to talk in a couple of seconds. But when you look in the central part here, we do see an edge-on galaxy, which is, sort of strange. It's a little bit off the center, but we also see a potential star, which we call the remnant star from a Type 1a explosion. One of the first things that the radio astronomers do when they get the radio observations, they look into a spectral index, and we're quite happy with this spectral index. It's a typical supernova remnant spectral index. You can see a couple of sources, background sources with a very steep or inverted spectrum, such as these two guys there. We also did a lot of filtering. As you can see on the bottom left corner, you can see that this looks like now starting to look like a bilateral supernova remnant. Well, there is something in the center here which we investigated, and it's quite possible it's just a background source of that edge-on galaxy. Another thing that we're doing in radio astronomy, and which is very much connected to supernova remnants, is to look into polarization. And to our big surprise, we couldn't find any signs of polarization. We do see a polarization from background sources, from a couple of background sources, but definitely nothing from there. That was a bit of a worry why we don't see any polarization. So we don't see anything there. So is this one of these orgs that we've seen? And this one is particularly huge and big. And the nickname was at the very beginning Uruk-hai as the biggest of all of them. So we investigated, could this be some sort of artifact from the narrow angle tail AGNs? Doesn't look like, it's quite possible to be that. We looked into possible precessions of AGN, which you look down the barrel. That doesn't look, again, a good idea, but we investigated that as well. So at the end, we concluded it's very unlikely to be this org, odd radio circle, because it's a much bigger spectral index is completely different than all other orgs. And at the moment, we have something like a dozens of these objects all around the sky. We don't have a particularly strong central source like all other of these orgs. No polarization, which was one of the biggest concern in general. So, well, what is left? The left is definitely to look into that is a supernova remnant, a hostless supernova remnant away from the LMC and maybe even from the Milky Way. Once again, there is no obvious optical or X-ray counterpart. We can explain that it's a typical size of SNR. If we take the distance to the LMC, it's just slightly bigger than the average size there, and it looks like a perfect circle. And you will see that in a second bilateral type. So only problem that we have is basically no polarization. We also looked into all other possibilities. This could be a type 1A or core collapse. So both options are on the table. Not that we can conclude. We have a slight preference towards the type 1A. And you can read it in our paper. I mentioned that there is a nearby star sitting on the ring here, and we investigated, could that star be something which we call the stellar super flare, with its M-dwarf nearby star, only 58.5 parsecs, but this would be a very much off the center explosion, and doesn't look a good idea that as well. And then we should see a proper motion, and we didn't see a proper motion, so we think it's very unlikely to be a baby orc or something related to a nearby explosion. So we think it's most likely to be a LMC SNR, galactic SNR, a little bit older. That's that's the two options. We are very sure that it's not a nearby star or a precessing BLX. If you have any other idea, please tell me. I'll be very happy to look into all this. So what's next? We're looking into parks to search for the pulsar there, looking for even deeper optical images. So we're looking for a meerkat, new optical observation. So this is the position of the object in relation to, on the left-hand side, Milky Way, and where the LMC is. Looks, quite stunning. So over the last couple of days, we got this stunning image from the meerkat. This is our LMC orc or LMC SNR. I'm now very confident. It looks like almost a perfect circle with a little bit of imperfection in this area here, southwest area, but otherwise it's absolutely beautiful. So another important thing is with the meerkat now we can see a polarization. This is a total intensity polarized image, and I'm quite happy now, and I'm sure that this must be a new SNR, very symmetric, very circular, and absolutely beautiful. The bad news is still that we use the CTIO 4-meter telescope. H-alpha didn't show absolutely anything, so there is no traces of H-alpha in any way or a format, and we need to answer why is that happening. So someone asked me, how similar is this? This is, something just, put together. It looks like very much to a Tycho to me, but it's probably a very different in any other way or a format. So that was all from me, guys. Questions?
Okay. Questions from yourself? Anyone have an idea what you think it might be?
I just want to say it's really strange and very interesting to find this kind of things.
My comment to that is I'm not that surprised anymore. I think, seeing a number of supernovas in external galaxies, and we should have a couple of these guys.
I mean, we know that we are probably missing a lot of nearby remnants just because they're low surface brightness. But they're quite beautiful, as you say, very perfectly circular and all that. Any questions in Slack or Zoom?
A question from Noam.
Yeah, there may be a
By some factor. Well, there are barrels. I mean, there are lots of supernova remnants in the Milky Way that have that.
Yeah,
especially more
classic example.
Well, not even not necessarily S10 to the particle acceleration, but in the radio, these older barrel remnants, that's thought to indicate the direction of the galactic magnetic field.
Yeah.
I mean, it looks like in older radio supernova, which is cool.
Yeah. Yeah. Okay. I'm not sure what your question is. two
Yes,
opposite
the
sides.
axisymmetry is that two opposite sides are faint and two opposite rims are brighter.
Oh,
It might,
it does-
it
it does-
might have an axis.
it does seem to have an axis, yeah. I don't know. Miroslav is the expert
But
here.
it might not be related to the explosion itself.
Yeah,
Maybe
right.
not.
You see that axis in lots of older radio supernova remnants in the Milky Way.
Which no one's fishing for.
Okay.
So very quickly, guys, someone asked about the Rosetta counterpart. No, we don't see the Rosetta counterpart at all. So there is nothing X-ray, nothing optical. And very quick info, I've seen a I think I've seen a paper from a Dutch group that they found from LOFAR, an SNR, which is most likely galactic with a pulsar close to the center, quite big, quite large. It looks like this orcish, ringish type, very far away from the galactic plane. So it looks like we have a few of these now.
We have ourselves a class. Okay, great. So our last talk of the evening is by Manami Sasaki. You there, Manami?
Yes,
Oh,
make sure I was. Oh, sorry. Where is it? Yeah, do you see the slide?
Yeah.
Yeah, okay. Yeah, so hello everyone. I'm Manami Sasaki. I'm from the University of Erlangen-Nuremberg in Germany, but currently I'm in Japan. That's why I am contributing to this workshop at this late hour for you. And thank you for being around. And yeah, I wished I could have been at the CFA, but yeah, unfortunately I couldn't. So I was asked to give a short overview of X-ray observations of supernova and supernova remnants. I'm very happy to give you a short summary, but as you will notice, and also as the time is limited, it will be only a very small selection and kind of biased selection. So I already would like to apologize for everything that is not covered here. Yeah, so let me start by talking a little bit about how X-ray emission was observed for supernovae. So the first observation of an X-ray source at the position of a supernova was already with Einstein for the supernova 1980K in a nearby spiral galaxy NGC 6949. So this was a mission, such a detection was already proposed before, but this was the first detection and was very exciting. And then after that, especially with the launch of Chandra and XMM Newton, and especially with the SWIFT satellite, the detection of X-rays increase significantly, as you can also see in this diagram on the right-hand side, which shows you the number of X-ray detected supernovae. And here are some examples where you can see the optical image or UV image of a galaxy. Both are like star-forming galaxies, and you have a supernova like in 2005 or 2006, and you clearly detect an X-ray source in the SWIFT data at the position of supernova. So this really helped us to understand also the supernova explosion mechanism and how the shocks develop in such explosion. So here's another sample of the X-ray detected or candidate detections. So as you can see on the left-hand side, you see a detection that was claimed with SWIFT, but then with follow-up observations with Chandra, these X-ray sources could be confirmed due to the high resolution, spatial resolution of Chandra. But if you look on the right-hand side, especially for those supernovae that occurred close to the center, the nuclear region of galaxies, it was quite difficult to resolve these sources with Swift XRT. So if you now then follow up with Chandra, you realize that the claimed X-ray emission actually is most likely not coming from the supernova. So this shows you the power of Chandra, the high resolution that we have in X-rays to also confirm or detect such emission from supernovae. And typically, if you see such early emission in X-rays, that's when the shock breaks out of the progenitor in the explosion. So this typically happens before the strong brightening happens in the other wavelength. So this is shown for one example, and a very interesting example where there was already an X-ray detection. And then you see the light curves in the optical and to the UV, and also infrared where you have the maximum and then the slow decrease. So you often see such a double peak like those cases. And this one example I also wanted to mention, and this is also related, for example, what JJ presented before. So this is a supernova that happened quite recently and is now among the class of double peak calcium-rich supernovae. So this is a new type of supernova that have been are being detected now. It has a high calcium to oxygen ratio in the optical, which means it has lower oxygen emission than compared to other remnants. Supernovae, and it also occurred in a nearby spiral galaxy M100. And there were also detections with Swift and right after the detection of the supernova, and also with Chandra, it has been confirmed. And you also see the light curves on the right-hand side. And this is a quite interesting example because the question is, what can make such a calcium-rich supernova also bright in X-rays? And as you might know, so there are different scenarios. Either this is like a type 1A with a white dwarf with an helium shell that's exploding, or a low mass star that has already lost the hydrogen envelope and then undergoes core collapse. So in any case, these such supernovae are also very interesting candidates for gravitational wave sources, because in any case you will have two compact objects most likely after such a supernova. And then in general, if you see X-ray emission from supernova remnants, what you see is that there is a strong shock wave that expands into the circumstellar medium and the interstellar medium. So the first X-ray flash is the shock breakout, and then it's the shock wave, which is in front of the shock ejector. The ejector thrown out ejector will expand in the circumstellar medium, and then later, when this supernova gets older and it starts interacting with the interstellar medium, we will clearly see it as an extended source that we call a supernova remnant. So in the early times, like the decades or even 100 years, the supernova or supernova remnant is mainly defined by what you have as a circumstellar medium. That's also what we heard from Katie before, and so therefore we can nicely study the mass loss, the evolution of the progenitor, and also the mass loss history of the progenitor. And the most known famous case is supernova 1987A in the LMC. There you see optical images before and after the supernova. You see this bright shining dot. And here most of you have already seen how it brightens. Then like 15 years later, it shows 16, 17 years later, it starts showing this bright ring around it. So that's where the shock wave the blast wave starts hitting some equatorial ring that was created by the progenitor. And if you look at the X-ray emission, so this is taken from a study by Frank et al. 2016 using Chandra. Again, thanks to Chandra's high resolution, you can see also the different emission, how the emission changes, and the X-ray emission changes with the evolution of the shock wave and the interaction with the equatorial ring. And since we can also separate the energy in X-rays, we can also see start seeing the different components. So as we have seen, like after 16 years or so, the ring starts brightening, and then you see this on the right hand side. That black is the total flux. You see that it's like a slowdown, and at that point. And then what you see is if you separate it in energy in red, what you have is the soft emission, and in blue you have the harder emission, and in green the medium. And you see that so that this shock slows down very significantly. So you can see it at this slope. Sorry, that's not the light curve. So it's the radius over the time. So it gets slower in green, and in blue and in black. I also said that in a wrong way. So red is the black is radio, blue is the hard X-rays, and there you see a similar evolution because hard X-rays traces the evolution of the outer shock wave. So this is now expanding through the ring and beyond it, and this is the typical velocity of the outer shock wave seems to be around 3,000 to 3,000 something kilometers per second. And that's also what you can see now. You have the light curve, sorry. Okay, so the light curve shown here on the top, where you see the soft emission that is dominating in the beginning because the ring, there is a lot of dense material. So there is this when it's shocked, it's very bright, but then it stays constant after it has been shocked completely. But then the hard emission shown in blue, it increases continuously. So that's the shocked ISM. And also the comparison, if you look at the different spectral components, you see that this harder component keeps increasing. And this is also what we could confirm using the newest XMM and eROSITA observation. Here you see an observation from 2019, I think. Here the orange spectrum is the XMM spectrum, and this lower spectrum is eROSITA spectrum, or TMs at telescope modules at that. I think this was the first light observation, and the spectra are very consistent, so it's fitted with the same model. And on the right hand side, you see a light curve created with rho Z and an X-ray XMM Newton for the softer band and the harder band, and also the measurements with eROSITA seen in shown in red. So it's very consistent, and we will be continue looking at the following this emission, this evolution. Right, and if you have such nice data in X-rays, of course you can also start comparing this with theoretical simulation. So that's work done by the group around Salvatore Orlando in Palermo. You see, assuming different models for the progenitor and the stellar wind, you can calculate the expected X-ray emission. So these are again light curves for different energy bands and showing different components like the ring component and the intercell medium component, and also trying to reproduce the morphology, which is very nicely in agreement with what we see in X-ray emission. And that helps then also not only the evolution of the supernova, or now almost the supernova remnant, but what happened before the explosion. Similarly, you can also study this circumstellar medium. In some cases, if you have a young bright remnant, like in the case of G292 or Cassiopeia A, very famous bright supernova remnant. If you look at the density profiles, for example, you can see that you can learn what stellar wind must have been, so what type of star you must have had before the explosion. Or you can also look at the spectrum. If you have a bright spectrum, bright enough spectrum with low extent that you can study it with the grating, then you can also, for example, determine the element abundances, like in the case of G296.1, and compare it with what you expect for the stellar winds. And what's shown here is the example G292, where you see the X-ray remnant and the position where the densities have been measured, and then compared to theoretical models for different distributed density profiles, assumed density profiles for the ejecta and the surrounding medium. And depending on the density distribution, the emission will also be different. And yeah, another example where you can nicely see the evolution of the supernova remnant is G1.9, which is a very young remnant located in the near galactic, close to the galactic center. It was detected as a very hard remnant, very obscured. And as you might have seen in the image, so you can, again, with the Chandra resolution, you can also see how the outer blast wave is expanding. This is also shown with these arrows in this image, not only in radio, but even in X-rays, we can observe that. Cassiopeia A, so that's this nice core collapse remnant that we all know. Here you clearly see the outer shock wave. It's mainly seen in the hard X-rays, and then you have the ejecta, the reverse shock heating the ejecta. We also heard a very nice talk by Martin Liming this morning about studying how what the element abundance distribution is. So this is here in the lower panel, you can also see, if you make narrow band images for different emission lines, you can also study the distribution of the elements, and especially for iron, you get these compact regions where you have higher emission. And also with Chandra, you can see the evolution of the reverse shock and also the ejecta clumps. So if you look at especially where these errors were, so you can see also the brightening and also fading of such ejecta knots. Similarly, you can also study the emission, and for example, in infrared, that has been done by Delaney et al. Already more than 10 years ago. You have so here you see some the strength of where you can detect the element emission for X-rays, so iron, silicon, but also argon that you see in infrared. And from the fitting, analyzing the lines, you get the dynamics, and you can reconstruct the 3D structure of Cassiopeia A. And so you can, this allows you also the dynamics of the reverse shock, the supernova remnant, but also the distribution of the elements inside. Tycho, which is not a core collapse, but where we can also nicely see how this is changing and expanding. And the nice thing about Tycho is here you really see this outer shock wave and the inner ejecta, how this is nicely mixing. And also, I mean, this happens both for all types of supernova remnants. And here you see some simulations also by J. Farron, where not only this hydrodynamics is taken into account, also particle acceleration in the shocks and how this mixing occurs between the shocked interstellar medium and the shocked ejecta, and nicely reproduces this diffuse inner structure that we nicely see in Tycho. In Tycho, we also see these magnetic stripes, which were detected by Chris Erickson, and in the harder band. So you see, so first of all, the outer regions, you see these very narrow lines where you have the outer blast wave, but you also see these narrow stripes, which must come from some amplification of magnetic fields. So it can either be some magnetic fields amplified due to this mixing of at the contact discontinuity between the ejector and the interstellar medium, where you have some turbulence going on. And there are also more recent studies carried out by Matsuda are also based on Chandra, and where they really studied each of these filaments and also the time variability of the filaments. So in this image here, upper left, you nicely see how this is expanding. So this is like a subtracted image, but then also you see how the filaments change. And here in the profile, flux profile, you also see how this is expanding, but also the inner parts are changing. And their conclusion is that these lines are most likely amplified magnetic fields, not inside, but in the outer blast wave. So some amplification of interstellar magnetic fields that are going on due to the outer shock wave and the particle acceleration. Now, of course, if you have some synchrotron emission magnetic fields, we expect polarized emission, and this is like I won't talk about it because I'm sure Pat will talk about it more in detail later. And yeah, so we now or even see polarization in X-rays. It's a very nice result, and it's very exciting. So in the future, we will be seeing more of the such confirmation of this magnetic field interaction in X-rays as well. Then I would also like to talk about a little bit of supernova remnants in other galaxies, especially the Large Magellanic Cloud, because that's where we can study the supernova remnants, or I mean, all kinds of populations of objects in detail, because it's nearby. We can look at it face on, so that's the newest image taken with the Rosita in X-ray. So you see all these sources looking as point sources, but then also diffuse emission coming from the interstellar medium. So we can now use this X-ray data. Of course, before that we also had a lot of XMM and Chandra data to study the entire supernova remnant population, like also what has been presented by Katie nicely. So similarly, what they have done in what they're doing in this SMC, we had an entire survey going on with XMM Newton, and so for the brighter and bigger remnants, we could do some spectral analysis, morphological analysis, and if we want to understand what the type of these remnants are, similarly to what Katie and her group did, we also looked at this stellar populations, and you see this star formation rate plotted for each of the, so these are selected remnants, and on the left hand side you see an N63A, which is a core collapse remnant. You clearly see that there is a high star formation going on in the not so long time ago, but then in cases where we see type 1A supernova remnants, typically there is no star formation in the past 10 millions of years, but then there are the region is full of older stars. So this is what we did with remnants in the LMC and also in the SMC, and by doing that we can also start it now separating the types. And here you see nicely a sequence of type 1A supernova remnants, and where you see from the top left to down bottom right, some kind of an evolution of the remnants. So they're sorted by age, and this thin line is always indicating 1 arc minute. So this is a very small remnant. This is a large remnant. What you nicely see is that at some point, so the remnant becomes diffuser and diffuser. You see here the shocked interstellar medium, and this bright emission in the center, that's all around 1 kilo electron volt. And that's mainly coming from the iron Elcher emission. So in the type 1a remnant, you often see the iron emission from the iron that was produced during the supernova. And again, also, as you heard, supernova remnant core collapse type are rather have different shapes. So here you see the well-known core collapse supernova remnants, and you see different shapes. It depends on the circumstellar mediums and also the interstellar medium. And I haven't talked at all about the plasma emission that we see in supernova remnants. But if you look at the spectra, you can also see how different the ionization properties is of the plasma inside the supernova remnant. That is shown and result by Hiroya Yamaguchi, where you can look at the line, in this case, iron K alpha line, look at the centroid, determine the ionization property, so if it's highly ionized or not. And then if you look so compare it also, look at the entire sample of supernova remnants, this is now galactic and LMC, and you nicely see a separation between the type 1a and core collapse. So this is also showing us that there is a density distribution and also different density distribution, especially for the core collapse. So this has an effect on the properties of the plasma inside the remnant. And most likely I'm running almost out of time, but let me also, just quickly show you. So luminosity function is also what you can look at if you compare different galaxies. And we also know at this point with the missions that we have, we look at the very bright remnants in the, of course, in the LMC, SMC, we can go down to very faint. But if we go to a more distant galaxy, we are limited by emission. And this, looking at luminosity function, you can also learn about the star formation history in the galaxy. So this is something we would really like to extend. And for that, for example, with eROSITA, we are now studying, performing a much deeper and more complete study of the supernova remnants. We have new candidates that we would like to study also in X-rays and most likely confirm. And then in the future, we will also hopefully have additional powerful missions that can help us to study, even go further with those studies like Athena, WFI, or AXIS. We can detect and study the supernova remnants even at higher distances. So here, this is an example of the brightest supernova remnant in the triangular galaxy M33. This is what you can already get with 10 kiloseconds with AXIS, and similarly also with Athena, WFI. So up to 2 megaparsecs, where there are like 20 galaxies or so, Southern galaxies, we'll be able to study the supernova remnant population in the same detail as for the LMCs we have been doing so far, and even go up to like 20 megaparsec and get all the brighter remnants with such spectral, for most of them spectral information. And we will also getting this high resolution spectra if we have, hopefully, pretty soon with GRISM, and then hopefully also with Athena Excifu. And with such a spectral resolution, we can even study the dynamics. Here you compare in blue the lines in the resolution of Excifu to the PN that we had so far in green for a simulation of Tycho. So we can study the 3D dynamics of supernova remnants, even for the not the closest one. And yeah, so I wanted to finish just to remind you about a call that I think in the US that came out yesterday or today. So the Athena will, as you might know, the future of Athena is not so secure. And there is a call for a new science redefinition team. So I would like you to encourage everyone, and I will do so as well, to apply to become member of this science redefinition team. For us in Europe, the deadline is end of September. In the US, it will be a little earlier, 2 weeks earlier. But I guess you all know the details. And yeah, I will finish with the summary slide. So with X-ray studies of supernova remnants, you can really learn a lot about the progenitor, the explosion, the nuclear synthesis that occurs both especially in the supernova, but also how elements are distributed in stellar winds, the shocks themselves, the physics of it. We also learned today that there's a lot of dust processing going on. So in supernova remnants, you can learn about that. Also comparing with the X-ray emission, which is also thermal emission. Ejecta and the interaction with the surroundings, which also is very important for the cosmic ray acceleration and star formation, and also like what you have seen in this image of Rosita, where you see a lot of hot interstellar plasma inside the galaxy, how this plasma is created in galaxies. And that's the end of my talk, and thank you for your attention.
Yes, thanks. So people have energy left for questions. Oh. That was a beautiful time. Any questions from the room?
One question about Rosita. When is data going to become public? And then has there been any progress on I know the Germans are committing to public open science, but the Russians have not yet. Is that correct?
Yes, that's correct. So I can only speak for the German side, and the German data, the first survey, ERAS-1 data, will be released most likely early next year. So whether it will be February, March, April, I cannot tell you. But in the first quarter of next year, most likely, the ERAS-1 data will be public with the corresponding software and calibration data.
So it's not a fixed schedule, but it's up to you once you guys are done with getting all the signs out.
No, that would be great, but yeah. No, so there is an agreement with the DLR, the German Space Center and Air. How is it called in English? I don't know, but the Deutsche Luft- und Raumfahrt. So there is an agreement that it has to be published early next year, and we're working on that.
I guess the Russians are busy with other things at the moment.
Yeah.
So as I said, I cannot tell you anything about the Russian side because we don't know either.
Okay, thank you.
Paul Pochinski mentioned February 2020 when I just asked him this last week. That's consistent with what you said, but maybe more specific or maybe less accurate.
February 2022.
3.
Next February.
So maybe it's February. Could it say that if it's Andrea, then he's more Andrea Meloni, he's more reliable than what I said.
As someone high up the pecking order. So Martin asked an interesting question. I see I think he's also online, so I don't know, maybe he wants to ask it in person, well, virtually.
The synchronous stars are due to the propagation of the circle.
I thought he has his hand raised. There you go. You can talk if you want, Martin.
Okay, great. Yeah, I was interested in your comments about the stripes in Tycho. I published a model in 2015 where the story is you have parallel propagating circularly polarized waves generated upstream of the shock by the highest energy cosmic rays. As
Yeah.
they go through the shock, the magnetosonic part of the circular polarization damps very quickly by transit time damping. So you just have a regular variation of the Alfvén wave behind the shock.
Mhm.
That gives you the stripes, the variation of magnetic field pressure in a regular behind the shock gives you the stripes, and you end up with cosmic ray energies of around, I don't know, 2 by 10 to the 15, I can't remember exactly. And so basically it's the interaction of a circularly polarized Alfvén wave. This is generated by the Bell instability, so it's not a random resonant Alfvén wave, but it's a monolithic macroscopic Alfvén wave going through the shock. And you know, it has to be an oblique shock so that you get the magnetosonic wave damped. And yes, you get cosmic ray energies around 2 by 10 to the 15 EV, as I remember right. It's the important point is that going through the shock, these waves can be amplified by huge amounts.
Yeah, it's thank you for the comment. I should have maybe included it. So I think this is kind of the reasoning that that's behind the interpretation of also of the new Chandra data. So that these stripes are indicative of what's happening in.
I think the stripes move. If you look at Tycho, that they're moving with the forward shock. So it must be connected to the forward shock. It can't be anything in the precursor.
I think that's how they interpret their results.
Actually, Una and I had done the same measurements that you showed, but we had never got around to writing it up.
Okay, I see.
So thank you.
Thank you.
Martin, can I ask you what that would predict for the X-ray polarization of the stripes?
You can ask, but it's a bit later. let me think about it. I think the stripes are polarized. As I recall, there should also be stripes in the precursor region the stripes are polarized. There will be stripes in the orthogonal direction in the precursor. I can't remember what the polarization properties will be. I have to think about it. I can't answer you offhand.
Okay. Let me
They
know
must be polarized because you've got a monolithic wave and a monolithic magnetic field. But I need to think a bit carefully about all the geometry.
It's okay to think about it and answer tomorrow.
Exactly.
Or
tomorrow.
Let me know if you come up with a thought.
But yes, it will be a good target for polarization observations.
Well, we've already looked at Tycho, that's why I'm asking.
Okay. Any more questions from the audience, from Slack? No? Yeah. JJ wants to set as an exam question, so there you go.
Excellent.
They're gonna be popular with the students. Okay, so thanks everyone. Thanks for staying until 10 p.m. At 13 hours, this is the longest conference day I remember. So anyway, call it a day. Thank you, everyone.
Thank you.
Thank you, Carlos.
You're welcome.
Bye.